In 1928, a 24-year-old Ukrainian physicist named George Gamow solved a mystery that had puzzled nuclear physicists for years. Radioactive nuclei were emitting particles with less energy than the barrier holding them in. By classical physics, they should have been trapped forever. There was simply not enough energy to escape. Gamow's answer: the particles did not go over the wall. They went through it. Not a metaphor. Not a simplification. The particles literally appeared on the other side of a barrier they could not classically cross. To understand how, you need to remember that quantum particles are described by wave functions. A wave function is a spread of probability. Even inside a classically forbidden region, a place where the particle cannot exist by energy conservation, the wave function does not simply stop. It decays exponentially, thinning as it penetrates deeper into the wall. But if the wall is thin enough, the wave function leaks through to the other side before it vanishes entirely. There is a non-zero probability of finding the particle outside the barrier. That probability is tunneling. The transmission probability depends exponentially on two things: how thick the barrier is, and how high it is relative to the particle's energy. Double the barrier thickness and the probability drops by a huge factor. This is why tunneling is easily observable at atomic scales but invisible at human scales. A baseball thrown at a wall will not tunnel through it, not because the physics is different, but because the barrier thickness in atomic units is so enormous that the probability is 10 to the negative power of something like 10 to the 25. You would wait longer than the age of the universe. Many ages. The most important tunneling event in the universe happens about 10 to the 38 times per second inside the Sun. Hydrogen fusion requires two protons to get close enough to fuse. But both protons are positively charged and repel each other. The temperature of the Sun's core is about 15 million Kelvin, impressive, but not nearly hot enough, by classical physics, for protons to overcome the electrostatic barrier. The Sun would burn out in about 10,000 years. Instead, it tunnels. The proton's wave functions overlap through the barrier, and with low but non-zero probability, they fuse. Tunneling is why the Sun shines. It is why you exist. Tunneling is not just astrophysics. The transistors in every computer chip use quantum tunneling deliberately. The flash memory in your phone stores data as electrons tunneled onto floating gate electrodes. The tunnel diode, invented in 1957, operates entirely by tunneling current. The scanning tunneling microscope, for which its inventors won the 1986 Nobel Prize, uses tunneling current to image individual atoms on surfaces. We have learned not only to observe tunneling but to engineer it at the scale of individual devices. Your computer runs on quantum weirdness. The truly strange thing about tunneling is not that it happens. It is what it implies about the nature of barriers. A wall is only a wall if the energy required to cross it is definite. In a quantum universe, energies are not definite in the way we imagine. The particle has a probability to be anywhere the wave function is non-zero. And the wave function, being a wave, does not stop at hard boundaries. It bleeds through. The universe's walls are not walls in the way your walls are walls. They are thick probability gradients. And every now and then, something finds the way through.